Okay. I'm back. Question is, will the stream? Okay, okay, so we are actually streaming something.
It's not the right view though, is it?
Yeah, like I think like my screen share should probably just be on full screen or something, if that's possible somehow. Okay, so we wait for the layout fix and then and actually, like, do we know if voice on stream works?
If what?
If like people can also hear me on stream?
Let me increase the volume.
And actually, like,
yes.
Okay, great, perfect. All right.
So do we mute everyone?
I mean,
are we supposed to interact during your talk? Or?
Yeah, I mean, I think you can just ask questions like on like whenever you feel like, basically. I think the same goes for people in the chat. So okay. So I mean this. So okay. So first of all, I think I kind of want to say thanks to Yellow and Statebox to hosting me on this channel. So this is my personal research that I've been doing since I think September or something of last year, somewhere around that time. And so to like give a quick intro, what is it about? It's about a proof assistant that has metaprogramming in like not as other proof assistants usually do with ACTA, for example, where you can just write arbitrary terms in your language, but you can also write, well, basically everything that you could write by hand, you can also generate with code, and you can modify everything about the language in the language itself, like within the language itself. That includes every basic piece of syntax. Like, for example, the way you write function application. Like that should be able to be modified. And kind of, so the original reason for doing this was that I wanted a language that can function basically as a way to write math down. And so, I mean, we have, of course, languages like Coq and ACTA that can do that, but you always, in these languages, have to like make compromises on notation. So you kind of have to write everything the way the language dictates you to do that. And mathematicians don't do that, right? If you write math and you don't like the way you have to write something, you define, well, I want to write this and mean this, and I just want to change basically the syntax of the language, and yeah, I just want to do that, and it should work, right? That's kind of the thing I was missing from those languages. So let me my cursor here. Okay, so that's basically for the intro. So now let's get started with like how it works and what we need to do. So first of all, the language itself is based on Cedille. Cedille is basically a small type theory that there are lots of good reasons to have Cedille around, and it's a really interesting project for itself. Not only because of the fact that it's small, but that was the original reason that I chose Cedille. So it's a very small type theory in which you can do induction, and that's that already is something that is unique about Cedille. Basically, basically most of the type theories we have today are based on the calculus of inductive constructions. I mean, most of the type theories that are implemented in theorem provers. So like ACTA, COG, Lean, all of those are based on the calculus of inductive constructions, which is an extension of calculus of constructions. And it turns out that adding inductive data types to the calculus of constructions makes it a huge thing. So it's really complicated to prove that the system actually is logically consistent. So yeah, it's kind of this behemoth, and I didn't want to implement this large thing to then just put like a small extension on top of it. And so this is something that Cedille is really good at. There are also some other reasons that Cedille is really good for what I want to do, and where it's like from my point of view better than these other systems. But yeah, smallness is basically the main reason. So the next, yeah, so maybe I should talk about two other big reasons. One of them is the proof that Cedille is logically consistent is sort of easy. It fits on, let's say, 5 pages or something. I don't remember exactly how long it is, but it's not that big of a proof compared to if you just want to prove that the calculus of inductive constructions is correct. If you look at that proof in the standard literature, I haven't actually counted pages, but I would probably estimate it right now to be like 20 or something. And so that's a really nice thing about Cedille, because this a smaller proof gives you basically, it makes it easier to extend that proof, right? I extend the theory a bit, and so yeah. Was there a question? Or okay, well, yeah, so that's one thing. The next thing is, I already say it here on the slide, Cedille is Turing complete. And that's actually really nice, because this means that not only can we use the system as a proof system, we can also use it as a programming language to write really arbitrary code. And this does not break our logic. And that's really nice to have, I think. So of course, then the question is, how much can we actually do with it? Like how nice is this Turing completeness to be used actually? But that's a different question. It's nice that it's just there in theory. And so, yeah, what do we have right now? We have these metaprogrammings in ACTA and Lean, and I mean, COG also has metaprogramming. But they are all kind of limited to just writing code or writing terms or other statements in the language and then just executing them. I mean, that's already really good. I think in ACTA, for example, you can get really nice stuff done. And I think Lean is even more powerful. But if you compare it, I think everybody who's used Lisp for a while, or any like Lisp language like Racket or something, it's just not comparable to Lisp. Like that kind of metaprogramming you can do in Lisp is just so much more powerful and so much more easy to use, actually. Yeah, it would be really nice to get something like Lisp, and that was the original goal. Like, try to get Lisp on top of this other stuff. Actually, I'm somewhat convinced that my final solution is stronger than what Lisp can do in its metaprogramming. Like, not from a theoretical viewpoint, but from a practical viewpoint. But yeah, we'll get to that. Yeah, so that's a goal. We need a really strong metaprogramming, which means that basically everything in the language should be accessible and modifiable in that language itself. And so to do that, I first set on kind of a bit smaller goal, because the big goal of like, what's the strong metaprogram? You can test for that, right? It's that's like an abstract goal, and you don't know when you will actually have it. And so the easier goal to go for there is I wanted, so I mean, Coq and Agda, and I assume Lean as well, have basically built-in natural numbers, which means that you write down your list of digits, and then the compiler knows, oh, okay, this is supposed to be a natural number. So even though the natural number type itself might not be built in, it would, for example, look in the context like, okay, is there a natural number type in the context? And if this is the case, then we will interpret this string of digits as a natural number. And so the goal really was, can I remove this feature and get it via metaprogramming? And so this is really the thing that I set out to do, and how I designed some of the things around. And yeah, so I kind of need to apologize on this slide. This is about the theory, and I wrote this nice LaTeX code in here, but I couldn't get, yeah, you can probably not view it at all on stream. I couldn't, so I wanted to get this done before the talk, but then we had lots of problems, so I couldn't make it in time. So the thing is, let me just talk you through it. So first of all, we extend Cedille with four term constructors. They are called m, mu, epsilon, and ev as an eval. So m is meant to be a monad with epsilon the unit, and mu is not the multiplication, but the monadic bind operation. And this monad is basically about executing calls to the environment of the language itself. So what you do, like the really important command here is the EV term. So for EV, what you do is you choose first two types, R and S, where S is the statement you want to execute, like the type of statements you want to execute, and R is the the type of possible results of that statement. And so the type checking rule here is that if you have a term t of type S, then EV of t should have type MR. So it should live in the metamonad, and it should be a value of type R. And the other rules are just for basically giving you all this monadic interface. So there's nothing really interesting there. And so I want to, I think I need to scroll a bit. I want to talk a bit about why this theory is consistent. And what you basically do, like if you know the proof that Cedille has a consistent theory, then what you do is you can basically extend that proof by just giving some extra rules for how this M type should behave. And then basically, so the proof of consistency means that you cannot prove false. And because the definition of the false type doesn't change, essentially this proof just carries over exactly like before. Yeah, I have a paper in the works where I will talk about that more in depth, how you would make this proof. But basically, the claim is that everything that I add to this theory lives within the metamonad. That's not strictly true. You can do some weird stuff, but it's almost true. And even where it's not true, you still are far away from the type false or from the empty type to still keep the consistency. So that's just a short, like, I'm not breaking the theory by adding these things. Okay, so enough about the theory. So how do you do this metaprogramming? Well, first of all, like if you have ever used metaprogramming in Agda or any of those other languages, it's kind of similar. You have this type S that was chosen before, and
by the way, Andre, 1 second. Can I ask you? Maybe I missed it because I had to walk away for a minute. But the Cedille, the language itself, did you give a sketch of it?
No, I just said, well, it's a nice language. The thing is,
could you maybe give me an idea of how it's different from Martin-Löf type theory or calculus of inductive constructions or something with W types? Or
yes, so you can view it as basically an extension of the calculus of constructions.
Yeah.
And it extends the calculus of constructions with 3 extra like term constructors. They are called iota, equality, and what's the third? The third is called I think erased abstraction or something. That's probably not the correct name, but so what they do is this erased abstraction type is basically a pi, but so basically a function type, but where you cannot refer to the variable you're binding inside the term you're actually using.
Okay, so it's like dependently tight, but you cannot use it in the term only at the type level.
So yeah, it's basically like irrelevant arguments, right? You can never use the arguments, otherwise the type checker will complain. And yeah, so I mean, you like basically for like an intuition, what you would do with this is, for example, if you bind some types, then usually you want your types to be erased. So you bind that with this erased abstraction. The iota is a dependent intersection type. That's a bit complicated. You basically want to, so if you have two types A and B, you can in Cedille form their intersection, which means, so Cedille isn't intrinsically typed, but extrinsically typed. So you have terms and then you assign them types later on. And so you can kind of imagine, like, if I give you a pure untyped lambda term, I might be able to assign it multiple types at the same time. And this is kind of what this intersection is about.
It can decidedly check whether this assignment is correct, like if you give an annotation.
Yes, because you basically to like construct an element in this dependent intersection, you basically need to show, like, I need to give you two elements, namely one of type A and one of type B of A. That's why it's called dependent intersection. The second type can depend on the first one.
Yeah.
So I give you these two elements, and they should, of course, type check in the correct way. So the first element should type check as A, and the second, like, small a, should type check as type big A, and small b should type check as B of small a.
I see.
And then you basically need to, and then what the type checker does is it throws away basically everything except the pure untyped lambda terms, and it checks if those two are equal with respect to beta eta equivalence, and that's how you prove something is an independent intersection. Yes, and so the third is equality, which basically just means exactly the same as I just said before. Two terms are equal if after erasing all the types, they are equal with respect to this beta eta equivalence.
Yeah.
And so as it turns out, and that's the major thing that is done in Cedille, is that if you have these three additional constructions, you can prove induction for church-encoded data types. So I mean, in the calculus of constructions, you have you can basically encode every like inductive or co-inductive data type. There exist these encodings for those data types, but the problem is that it's actually provably impossible to get induction within the calculus of constructions.
Okay.
And so if you add these three things to your theory, then you are able to get induction out of that. That's a bit involved, and I mean, I could talk about this, but that's like another 20 minutes or something. So
that's fine.
we might want to move on. But
okay, thanks. I have a good idea of how this language works. Thanks.
Yes. Yeah. So it's a really cool thing, and it's kind of hard to understand why it works, but it's amazing to see like that it works basically. Yes. All right. So back to metaprogramming. So we have this type S that features all the statements that we can execute in that language. And that is basically, like, in the code itself, I have just a long list, like a huge, well, not huge, but I have an inductive data types with, I don't know, 6, 7, 8 constructors or something that basically represent all these core statements. And this is like, all you can do is execute those statements in the language. There is nothing else that you can do. And so I just basically have the same type built in the theory, like within the type theory I implemented, right? So you just also like church encode this S data type, And like at this point, I don't have induction, but I can add it later. That's not a big issue. So yeah, this type S describes really everything you can do. And so how does it work exactly? You first have a parser. This parser is I will tell you later how exactly I specify a parser, but this is basically like a context-free grammar. A bit like it's not, you cannot put every context-free grammar in there, but only LL1 grammars, which are like a reasonable, easy to parse subset, let's say. And so this parser goes over the code you want to run, right? And so the result of parsing is a data type. Actually, well, the first step is you get a tree of parsing rules, which you basically apply, right? So you parse some code, you get first a tree, how to derive that stuff. And so the core idea behind this parsing concept is that it would be nice if I can turn this parsing tree into some values of some type T. So how do we do this? Well, the parsing rules are just strings, right? They tell you, okay, if I want to read some term, for example, then if it's a lambda, for example, well, it should begin with a lambda symbol, and then some other stuff should be after that, and it should contain like some terms for like types and the subterms and so on. So this is just a string that describes how to parse this lambda abstraction. But it also, at the same time, this string describes how the string refers to a function in the environment of the in the environment of the language itself. So, and that the name of that function is exactly the parsing rule, right? So I read something from a parsing rule. I have registered beforehand like what parsing rules I want to use, but it also already contains like it also already references a function or like a value inside my language. And so, well, now I have a tree where every element in that tree corresponds to a function in my language. And what I can just do is, if I have a node and it has 3 children, well, those 3 children basically are subtrees, right? And so those subtrees, I can. So this is where I do recursion. I want to now compute the like corresponding thing in my language that corresponds to the subtree, and then I just apply my function on that original node to all those values I got. So if I'm at the bottom, it just the parsing rule just gives me some value in my language, and then one step above is like I apply a function to all the values that have been generated at the bottom. And so I can turn a parsing tree into the value of some data type T. I don't care actually like what data type this is supposed to be, and all those intermediate type, like all the functions that, or all the things that are generated by this by smaller subtrees, they don't need to be of this type T. I don't, at this point, I don't care what the types are. What I care about is that at the end, when I type check this term I've constructed out of my tree, this final term should have type T. And that's what I do. I pass some code. I get some parsing tree. I turn that into some term. by just applying all the subtree stuff. And then at the end, I have a term. I can type check that and see if it has that pre-specified type T. And so now in the next step, I have this eval function that takes my thing of type T and turns it into some m T prime. And I don't really care about this T prime because if I just do like parsing with it, I will just drop it at the end. But because this lives now in this meta monad, I can execute statements from this original type S. So from within this eval function, I can now call this EV thing from the previous stuff. So within this eval function, I can make arbitrary, I can write arbitrary code and like execute arbitrary code basically. And yes, and so then of course, if I just wanna like execute something, I don't really care about the return value, but maybe, so you could, for example, imagine that T prime could return some error messages or something. And if I want to use that eval function later to write, say, a different eval function on top of it, then I might be interested in whatever error this throws. So, or like, if it throws an error, then maybe I want to do something about that. And this is why it returns some other type T prime. Yes, and so all these things we can change. So this type eval, this function eval, this type T, both of that we can just change. And we do that via a statement that's called set eval. You just give it a name and a type. Actually, you give it the name of what your new top-level type should be. You give it the name of the evaluator you want to use, and then you're fine. So in particular, you can change like how to parse stuff, and you can change how to evaluate stuff without changing, like without rebinding names, right? So you don't mess with the type checker in any way, or like the previous environment in any way. And so I think this is, yes. Okay, let me stay here for a bit, because I didn't really get to finish this. So the question is now, of course, how do you write parsing rules? And well, as I already said, parsing, like the parsing rules just correspond to names of some functions. And so you basically throw some functions in a namespace, where namespace isn't really a thing that is hard-coded in any way. Namespace just means I prefix the names with something. I don't care. And so you also, to this setEval function, you also give it the namespace. And then it will just take all functions in that namespace and use the names of these functions for parsing rules. And so I have special syntax, how like non-terminal symbols and everything should be like referred to within those names. And yeah, then basically the parsing rules are just names in the language itself. So there is no extra like data structure or anything for parsing rules. You can actually do that though. You could, for example, set your evaluator in such a way that it basically collects everything that you define and then just like keeps a list of all the stuff around that could be parsing rules, and then that way you can actually modify lists of parsing rules within the language itself. So it's not built in, but I'm pretty confident that you can actually add that later as you want. All right. So I hope I haven't really lost most people. So let's go for the demo. Ignore the error message here at the top. This is just, I don't actually remember. It's probably because it like tries to run something empty or whatever. Like it's not really a big deal. So this is the interpreter. It's just some REPL. The syntax is kind of easy. So you can, for example, define some x, and this REPL, like this, contains basically nothing. What's something that I can do? I can, for example, do I can do this. So init $term is just the type of terms, and yeah. So this is kind of what you can do. You can write let. You can also do normalize. I'm not gonna normalize x because that would print, I don't know, 200 lines or something. Because that's a really huge thing. But yes, so one thing you might notice from the above, so this is already, all these long weird names you see are already all these parsing rules. That's the syntax for parsing rules. So one thing is that these square brackets mean function application. The reason for that being not like the usual nice syntax where you just write stuff next to each other is because of my grammar restrictions. Right? I previously mentioned that I implemented the LL1 grammars, and so the thing that's required for an LL1 grammar is that basically the parser can read one character, and then it needs to decide what the next parsing rule is. And this basically means that everything like has to be prefixed in some way, and you can only decide with the first character and the prefix what you can actually do. So for example, what I cannot do right now, I mean, I might want to try to define something called let2, and I don't know what it should do, but I could try to define this, and if I do it naively, then it won't work, right? Because as soon as it reads the L, it has to, it has already have to know what to do with it, how to parse it. You can, of course, get around that via some cute little tricks, but yeah. And so, okay, so this is just the core language. I didn't load anything here. So basically, I can just write some lambdas, some function application, and every other basic term, and that's it. So let's move on to this. So you already see, like if I go through here, I imported like a lot. I did a ton of stuff here. So this loads basically all the test code I've written. And in particular, it loads the ability to write natural numbers. So this is just, I imported a single file, which of course then also imported other files, but this is really exactly the same thing. I just import one, I just run one import to start all this up. And this code, by the way, is on GitHub, so you can run it yourself. And so basically, you can see here this this last term basically defines the rule for passing natural numbers. This is actually currently it only reads binary, so we don't do decimal. But I mean, that's just a restriction because I didn't want to write extra code for now, because that's just a small demo. And so it means basically that if so this init $ at the beginning, it's just the namespace prefix. Afterwards, we have the non-terminal symbol that we want to use to parse. So this means if I want to parse a term, I can use whatever is behind the $. And the syntax afterwards, so the thing encased in equalities is a new. So this means that to use this rule, I should first use a new character, and then afterwards I use a bin nut, which should be like the natural number. Like this is the thing where we pass now instead a binary natural number. So this is almost what I wanted in the beginning. So let's do it. Let's do, like, I don't know, this. So let's see what we can read from this. First of all, I apply this parsing rule, and now this gets translated into some code. You can see the code to the left here. Basically to the left of this column. So there's this function bool list to nut, which takes a list of bools and converts it to the appropriate natural number, basically via just iterating over it once and multiplying by 2 and adding 1 if necessary. So that's just like a regular fold like you would do in every other language. And afterwards, you can see how the list is defined, right? So you have this cons function. The square angle brackets, by the way, are erased application. So that's kind of what I mentioned previously. We have this type bool that we want to refer to, and this here is referred to with an erased application. And so then this t there is just the Boolean value for true, and of course false is f. So this means that we apply the function bool list to nut to a list of 3 elements. All of them are t. Maybe I should have like 101 or something. So now you can see that in the middle we have an f now, and then it says, well, this term normalizes 2, and then you get like a huge stack of lambdas. So the reason here you get this huge stack of lambdas is that this is you really get the lambda encoding of these natural numbers. So yeah, it just looks like that. It's actually not directly the church encoding. That would look slightly different, but it's certainly an encoding of natural numbers. And so we can actually, I think I can show you, for example, how the number 2 looks like. This is, so 2 is really defined as the, you can see it, you can see it up here. So 2 is defined as the successor of 1, 1 is defined as the successor of 0. And so you can kind of see that this 2 is actually has kind of the same structure as the stuff below there. And we can actually check if this encoding is correct. So you can, I mean, just empirically. So we can, I talked about before that Cedille has this erasure type. And so I'm not really going to talk about what this beta means here. But I want to prove now that this 2 that are defined up there as the successor of 1 is exactly equal to the 2 I defined via the new, right? So maybe let's make brackets here. If I start with this equal sign, this means I'm talking about the equality type. And so I want to prove that 2 is equal to new of 1, 0, right? And so let's do this, and the type checks. Let's maybe just to show that if I put like a 3 here, then I should get an error message. So this is actually running really slower than I expected it to. Okay, I didn't try that out before. That's interesting.
Well, if it keeps running, you'll probably get an error message. So.
Yes. So I'm actually wondering now if I get an error message or if I somehow did something incredibly wrong and now we're in an infinite loop. That's interesting. But at least you can see like it really has a different behavior. So okay, I probably found a bug here. It shouldn't be that slow. Like it's slow. If you load all this code up that I loaded from this one file on my machine, I think it takes like 1.5 to 2 minutes. So it's slow right now, but I didn't really optimize all that much in performance. So that's kind of expected.
It's type checking while it's parsing, or?
Huh?
Is it type checking while it's parsing, or is it like a multi-row for AST, or?
So I mean, parsing shouldn't be the issue here, right? Because the thing before also parsed really quickly, and so.
Yeah, I was just wondering if it's like separate phases where you first parse it.
Yes. Yeah. So I have a parsing step, then I have several type checking steps in that scenario, right? Because of the metaprogramming thing. So this already runs completely on this metaprogramming foundation that I talked about. Like I parse this code, and then it will exactly turn into this parsing tree. Then from there, it gets turned into functions that get applied to each other. Then from there, I apply the evaluator. Then I type check the thing to see that this even makes sense to call all these functions and the evaluator on top of each other. And then after that, I can finally like execute this stuff. So let's just kill this. I don't think there's anything that will happen from here on out. Okay, so at this point, like I would argue that the original goal of being able to parse natural numbers from here is kind of successful, right? I mean, we have this new prefix, which I could actually get rid of even within the current parsing restrictions, but it would probably like be another couple hours of work to make that happen. So I'm not going to do that for now. So the question is now, what else can you do with this? How powerful is this theory or basically this metaprogramming language. And so let's get back to the slides. Yes, so minor caveat here, of course, is that this mu in the beginning, and well, technically I only implemented binary, but that's of course not like an actual restriction here. And so now we get to the part where my slides get kind of messy, because I think some of the stuff I've been doing previously got destroyed in the reboot. So let's skip to let's skip to here. So this is interesting. So in most of the, you cannot hear me at the moment. How about other people? Can other people hear me? Okay, Marco can hear you. Can hear me. So I assume that you can also hear me on stream. So okay, so I think I'm just going to continue. So one thing that you can do in languages like Idris or Agda is, or even COP, is you define setoids, and they will then you basically get some weaker form of quotient inductive types. You don't get real quotient inductive types, but you technically, like if you use setoids everywhere without a single failure, then your theory would probably look as if it had quotient inductive types. And so what you can do is, if you have this kind of metaprogramming available, and you have already like formalized how to write down inductive types. Oh, I kind of skipped ahead of that. Inductive types should also be possible with this metaprogramming theory, right? Because inductive types in Cedille are just, you write down, you define a term, right? And then you have an inductive type already. From there, you of course then need to define something like induction, but you can also like just write down all the definitions via metaprogramming. Like that's not something that's, I mean, it's not easy to write down the code, but it's not conceptually hard. You could do this in Agda. So like if Agda had all these things, of course. Inductive types should certainly be possible, but also from there, like you can define setoids, and then you could basically hide all these definitions for inductive types without an equality equivalence relation on top, and hide all the Cedille, like the core theory of Cedille. So you hide the basically everything that's not in the calculus of constructions already, and then it seems like you would have a theory with quotient inductive types. And so similarly, you should in general be able to formalize your favorite theory. So by favorite theory, I mean like foundational mathematical theory. So I mean homotopy type theory, for example, or the elementary theory of category sets, or even something crazy like Topos theory stuff. And so, I mean, because Cedille has lots of has all this calculus constructions basically as a sublanguage, you should be able to formalize all these theories within Cedille. And then with the metaprogramming, you just hide all the old theory that you don't wanna use, and instead expose nice syntax for your new theory that you wanna use now. And then from there, you basically swapped out your entire underlying theory. I mean, technically, your entire underlying theory is still Cedille, but you can hide everything about it. There is nothing that really tells you that you were in the Cedille theory once. So, of course, that's kind of speculative because I haven't actually written that code yet. But yeah, that was actually also one of the design goals. Like, so that's basically that's also, of course, something that you can test, right? And so that's basically what I originally wanted to reach with this idea of strong metaprogramming. But of course, it takes way more time to test than this basic natural numbers example. So that's not done for now. So this is really nice. You can also potentially do some things that are actually completely impossible with improved assistance. For example, in all the languages we currently have, you cannot reason about asymptotic behavior of functions, like runtime, for example. And it seems like this would be possible within this theory. We talked about that. Yes, reasoning about performance. So how would you do this? Well, you could add, you could basically say, well, I want to count, for example, how often I want to do addition or recursion in a function, right? So I want to write down my function regularly, and then I want to use my metaprogramming feature to basically say, well, this let statement that I used to define my function should now not only define this function, but it should also keep the term around that was used to define the function originally. And from that original term, you can now write some program that transforms your original code into a new function that has as its output type basically the same old output type, but you wrap a like a writer monad on the outside, and then every time you do recursion, you just add one to this writer monad. There might be some issues that like make this a bit complicated to actually automate this thing, but again, it seems to be possible. And then, of course, you can suddenly reason about your function, as long as you're convinced that your original code was correct. That makes this transformation from your original code to the annotated code. As long as you trust this code, you should now be able to reason about the runtime performance of this function, because this is now an output of your function. And yes, so of course, then the question is, how do you write this down with a nice syntax and everything? But yeah, that's like a different question, I guess. Yes. So, all right. At this point, I reached the end of my slides. So I hope I've given everyone in here some idea of what this all is about. So if there are any other questions, something that I forgot that I wanted to talk about. Something else that you can potentially do is give the user the ability to write their own algorithms to do things such as type inference or type class. Inference basically. And not type inference. Sorry. Type inference as well, but I'm thinking right now about arguments, like implicit arguments, and the unification algorithms for that, right? Because you can you have the code that you want to compile or you want to type check available during or before you actually type check it. So you can do things such as you give me some code, and before I pass it on to the type checker, I add some annotations, for example, to it to make a type check, or like try to guess some arguments that should go somewhere. And all these algorithms are then, in theory, be able to just import it via some library. So this would give you a lot of flexibility to work with, like to try out how good certain algorithms are, or if it works for the code that you want to use, all these things. So you like there is this chance that it doesn't need to be built in, right? You don't need to build these algorithms in the language itself. You just put it in a library, and that's really nice because if somebody comes around has a better algorithm, they just publish a library and you can already use it. There is no talking about, okay, this is really better, we should merge it into the stuff and then release it in the official release. But maybe this new type algorithm, like this new algorithm, breaks something that worked previously, and so like you have all these issues if you put it in there and hard code it within the language. But if it's just a library you want to import, then it's really easy to get new language features, things such as better syntax, better inference algorithms, all these things.
There's interesting tactics as well. Yes,
exactly. Like there is, I think there's lots of potential there to just make experiments with the language itself that you can't really do in most other languages. I think this is something that you can basically do in Lisp to a certain degree.
Mm-hmm.
But so far,
Lisp is not.
Yes, so far it seems like if you're not a Lisp, then you don't have this this general idea available.
Yeah. Interesting. I don't know if anybody has any questions.
So by the way, somebody said that something was mentioned in the Twitch chat. I haven't seen anything on there, so I don't know.
Do you see the message?
I don't see anything.
So Dwarf Planet Tossing writes, just got here and missed most of this talk. I was wondering what a more fully worked example of a quotient would look like, such as cyclical lists. So A, B, C equals B, C, A equals C, A, B.
Okay, yeah. So so what you would do is you have your inductive data types, and on top of that, so a setoid is basically a type A together with an equivalence relation on A. So you would then basically just take lists, like take the type of lists, and add this cyclic equivalent, like this equivalence relation where precisely the things that you want to be equal should be related via this equivalence relation. And So the idea is then that if you have, if you basically hide the entire regular inductive data types behind your theory or your metaprogramming, and there is no access for, let's say, library authors or something to this underlying inductive data type thing, then they are basically forced to support setoids on everything, right? So they cannot use inductive data types. Everything has to be a setoid, and in particular, every syntax that might be annoying to use. So, for example, if you have tried using setoids in Agda, and if you write down arrows like functions between setoids, and you want
Setoids are annoying.
Huh?
Setoids are annoying to work with.
Yes, yeah. So if you have two setoids A, B, and then you want to like have the function type A to B, I'm not sure if it's with function types, but certain, like there are different kinds of function types between those setoids you can have, and certain of those function types basically aren't actually types. So you would write down something like A arrow B, and then you get a complaint from the compiler that A arrow B is not actually a set. In Agda, it's called set. I'm not sure if it's for simple like A arrow B, but I have seen this message before, and it's really annoying. And you don't want that, right? You just want to write down the arrow because that should be a set. That should be treated like regular functions, and you don't want to suddenly like use special Unicode arrows and all this stuff.
But how would you do this in this proof assistant? Like, can you write down like a set with, let's say, 3 elements and a cyclic equivalence relation, or like a
not within, let's say, 5 hours or something. Okay, maybe not that long, but so currently I have no nice syntax for inductive data types, so I would basically have to write all this church encoding stuff by hand, and that takes a really long time.
Mm-hmm.
What I have actually built, what I have not yet released, is a way to transform regular Cedille code into the syntax I'm using. So in particular, you can write Cedille code with the nice editor features that Cedille mode is offering, which I'm a big fan, actually. I think it's really, really good. And then from there, you can basically export it. It's a 2-step thing because I was lazy. So you can first export it to Cedille core and then use the thing that I've built, which is actually just a slight modification of the Cedille core Haskell code. And this will output you code that can then be just used by my language. So in particular, like if you look at, let me show you this. No, it's not here. Like if you look at this stuff here that I'm currently showing on screen, I didn't write that myself. Like that's.
I hope not.
I used Cedille. I used Cedille mode, and then I just exported the stuff. And yeah, it generates huge code, but I don't care, right? It type checks. It type checks exactly the way I want to.
Just add a few rainbow parents, and it will be legible.
Yes, I've written like a very small syntax highlighting mode for Emacs, but yeah, it doesn't work in the REPL yet. So it only works in source code, and I actually even haven't actually loaded that. So yeah.
Okay.
But yeah. All right.
Cool.
So if there are any other questions, you can either ask me now, or I guess I think the repository. I hope everyone knows where they can find the repository for this code. and so you can play around with it, and yeah, then you can also find me there, I guess.
Yep.
And of course on this Cedille mailing list, right? I will be reading that as well.
Cool.
All right. Yeah. Cool. Then.
Yeah, let's paste the repository in the chat.
Yes.
On Twitch. I just closed it.
Let me. Where is it? Or do you have it quicker than me? So. I'm not plugged in here. I have. Oh no,
there, exactly.
You have
that one. Make us a deal.
Okay, great. Yeah, for some reason I don't see anything on the chat. But okay, great. That's you already got it. Okay.
Somebody, can you see the chat?
No, I don't. I don't see the Twitch chat.
So, Mbakterev, I don't know how to pronounce his name, says, or her name, I am from supercomputing community. Will this somehow work with floats? Can we get some informative type from numeric algorithms?
Yes, something that I actually forgot, like that I also wanted to mention, but then completely forgot about. So the question is, I mean, okay, floats of course are a cool thing. Maybe the question before that is, how do you compile this stuff? How do you run this code? And so the idea is that because you have this, so first of all, you have this erasure mechanism, right, which turns your code into untyped lambda calculus. And well, untyped lambda calculus is basic. I mean, it's basically really easy to compile already. You can basically turn that into some Lisp code, for example. That should be a really easy translation, and go from there. And what you would do then at the next step, so you of course don't want to compute with any church encoded data, right? That's horribly bad. You don't want to have exponential runtime for like addition or something. So what you would do then next is to run to basically say, well, I want to, whenever I refer to a natural number, I want to instead refer to the built-in data type within, I don't know, let's say I use scheme, for example, to compile my code. Then I would just point to the internal data type of scheme for natural numbers and just say, let's use that instead. And then stuff like zero function, successor function, addition, and so on, you would basically like make a map of like how do you map this function to this other built-in function. And so you would be able, for example, to compile this code to something that's reasonably fast.
Like a FFI kind of.
Well, not really. So what you would actually do is, I haven't talked about what statements are like I have built in. So one statement I have actually built in is a system call statement. So you can actually run arbitrary calls to your shell. And from that, you can even get the string that it returns and do something based on that string within the meta monad. And so from there, what you would actually do is you would basically first write like a pure function that translates your lambda terms into a string, then call the scheme compiler, for example, with that string, and then you have an output program.
Right.
So
actually, so there's another remark on the Twitch chat. Worksblock asks if you are familiar with github.com/monad with double O /formality, capital F.
Yes. Kind of.
And then he says, I know the author was working on a language based on Cedille that would compile to this, but this might be outdated. I actually thought you were the same person having just tuned in and hearing Cedille. Yeah, so look, we are working, Andre is showing his work on a proof assistant based on Cedille.
Yes. So I think formality is made like, I think Victor Meyer was the person working on formality. Not 100% sure on that, but
oh, so it's a fork.
Maybe I don't know. But yeah, I have seen it. Yes. I think it's a really cool thing. Also, I mean, there's lots of stuff to explore in the space, right? So I'm really interested in seeing where all this stuff goes.
Oh yeah, it's from Victor Meyer. Cool.
All right.
So yeah, well, thanks.
Yes.
We have a recording of it as well, so I'll put that online. And yeah.
Yeah, that's really cool.
It was cool to see. Nice.
Yeah. Then thanks for listening to my talk, everyone. And
Lux Block. Oh, Bok. Lux Bok. Okay. Yeah, man, these names. Luxbox says, yes, that is correct. I mentioned this because formality, or maybe it was a different project within the same umbrella, is actually a compilation target for a lambda calculus-based language that tries to avoid the need for a garbage collector.
Yes, I think this is the work on the abstract algorithm, right? So yeah, that's also really interesting. So I mean, scheme was just like the first thing that came to mind. Of course, if you have like a really good target to compile lambda calculus to, that would be, of course, nicer. Yeah, but I guess you'll just have to experiment with it.
Yeah, cool. What are your next steps going to be?
So next steps would be to, first of all, my to-do list has, I think, still 3 items. There are some top-level statements that I still want to implement. They're kind of small and easy to do, but I haven't gotten around to that yet. Currently, the import command is built in, and what I want to do actually is replace this by a. So what you cannot do right now is specify a string and parse that string into something directly, right? You can only do that if you like import it from a file or something.
Yeah.
And this currently, I mean, I just need to wire some stuff up correctly. It's not like a big deal to do that. But yeah, so this is something that I still need to do. And then from there, I think actually the next step would be trying to get maybe a bit nicer syntax at first. So I'm thinking about a Lisp-like syntax because it's like is so Lisp is a LL1 parsable syntax, right? So I cannot really do some Haskell-like syntax or something because the parser is just at this point not capable enough. But I can do something like Lisp, and I mean that would already be a huge upgrade from what I'm currently using. And then, of course, inductive data types. So basic support for inductive data types and a library for metaprogramming. So I've already started on that, but yeah, the idea is basically you wanna. So currently, if you wanna code something, then that's really ugly. I can actually show you this. Where is it? I think it's tests and then list tests. And yes, so for example, in this line, you can see you can see I want to quote the name bool, right? I want to be able to basically write the term. No, I want to quote the name true. I want to refer within a term to the variable defined by the name t. And so the only way to do that is basically to write a list of letters. This is what this quote $t is doing. And so I can only write every single letter on its own. And that's, of course, a really bad syntax, right? In Lisp, you would just write quote t, and you're done.
Yeah.
And so this syntax is really annoying. And then, of course, if you get to longer names, where like here we quote nil and cons, that's really annoying. And then somewhere is yes, we have this function bool list to nut that I use to convert a list of booleans to a natural number. And yeah, then you just can't read that, right? That's really annoying. So we want to have some good syntax for that.
Yeah.
And of course, like also syntax for strings, for example.
Yeah.
These things all have the like higher priority right now. And so I don't really know in what order this will happen, but yeah, that's kind of what I want to do right now on this project.
Okay. Well, cool. So thanks a lot, and
yeah, thanks also for hosting me.
Yeah, no, this was fun. One more remark was on the stream, a reference to double hash dependent on Freenode, the IRC channel.
Double hash dependent without like types or something?
Yeah.
Okay, I am not aware of this channel.
No, neither am I. Check it out.
Dependent. All right, I just wrote it down. I think dependently typed language and languages and related systems. Okay, yeah. I think I'll have a look at that.
Cool. All right, then see you around.
Yes.
Bye, everyone on the stream.
Bye.